So this lesson's on volume of solids with known cross sections. You guys should have the handout that I gave to you in class. It should look like this. It's the first page. Um, and there are three main parts to it. So there's an activity on a cross section that we'll do at the start, and then we'll get into the actual learning objective, which is main learning objective, which is to find the volume of a solid with known cross sections. And then so that's part of the classwork. We'll do some examples, and then there is homework. So the homework page looks like this. I have a little more writing on your copy where there's some point A and point B here is listed for you, so that's on your version. So that's the homework. That's part one of the homework, and the second part is to make sure that you know how to find intersection points with the graphing calculator. So in these problems, I had already given you the intersection points, but you really should know how to find those on your own. So there's the second part of the homework where you guys should watch these two videos. If you're out on that day when we did lesson area, or if this looks completely unfamiliar to you and you don't know what this is about, then you should watch these two videos to make sure you know how to find intersection points using your graphing calculator. And there's definitely going to be a mini quiz on Monday just to make sure that you guys are able to meet the learning objective, and also make sure that you knew how you took the time to look up these videos and actually learn how to find intersection points. So those are the three main parts. So the three main learning objectives for this lesson is to identify what the cross section of a solid is. So we're talking about, we'll see some examples of what a cross section of a solid is. Two is to understand the relationship between the area of a solid's cross section and the solid's volume. And then three, be able to, with that understanding of that relationship, write an integral expression that will compute the volume of the solid. So those are the three main things. So by the end of the lesson, you should make sure that you know you are able to describe your ability to meet each of these three learning objectives. So the first So the next thing I want to talk about is what a solid is, because the question will ask to find the area of a solid. So a solid is just essentially a three-dimensional object. So these are some examples of solids that you guys are probably familiar with. So this is a cylinder. This is another cylinder. Here is a triangular prism. You have a rectangular prism. And here we have a pyramid. And you have a cone. And you also have a sphere. So these are just called, the general term is solid just for a three-dimensional object. So the idea is that we're going to be trying to find the area of these solids using integration. So the next part we'll talk about is to know what the cross section of a solid is. So I'm going to play a video that'll explain that part.
Math Shorts. Slicing solid, three-dimensional figures results in different two-dimensional shapes, depending on how you slice them. If you cut through a cylinder with a geometric plane parallel to the cylinder's base, the two-dimensional cross-section is a circle. Any way you slice it, you can get two-dimensional shapes from three-dimensional figures. When you slice a cylinder from top to bottom that is perpendicular to its base, then look at the cross-section straight on. You get a rectangle. What happens when you slice a square pyramid? If you slice across the pyramid with your plane parallel to the pyramid's base, the cross section is a square. If you slice with your plane perpendicular to the pyramid's base, the cross section is a triangle. Remember, you're slicing a solid, three-dimensional figure with a geometric plane. You can slice in any direction. Just keep in mind that shapes can look different when you look at them from different angles. So orient the cross section on the geometric plane. Slicing diagonally can produce different shapes, such as an ellipse or a trapezoid. Understanding the two-dimensional shapes that result from slicing solid, three-dimensional figures is important for geometry and ninjas.
Oops. Yeah. So the cross section you can see is just the shape, the two-dimensional shape that results when you slice a solid at a certain angle. So for our purposes, we'll always slice the solid perpendicular to the floor in this case. Okay, so it always cut down in this direction, straight down, perpendicular to the floor or to your table. So in this case, if you have a rectangular prism that looks like this, if you slice perpendicular, the perpendicular to the floor, what would the shape of your cross section be? Well, in this case, if you cut it down, you're going to get a cross section that's a square. If you have a triangular prism that looks like this, if I make a slice down as if I was cutting bread perpendicular to the floor, then my cross section will be a triangle in this case. If I have this solid, so this half a sphere, and I cut perpendicular to the floor, I would have a semicircle. And then for the last example, if you have a cylinder that looks like this, and I make a slice down, then my cross section will look like a circle, or would be a circle. So that's what a cross section is. So you should know what a cross section is, but you need to know what a cross section is, but you'll always know what the cross section is in these volume problems that always tell you whether cross section is a square, a circle, a semicircle, or a triangle. But you should be able to visualize to a certain extent what the cross section should look like, and know that the cross sections will always be perpendicular to the x-axis. So I just went over the cross-section part. We can't do the Play-Doh activity here, but hopefully you guys got the point as to what a cross-section is. So here, just as a quick fill-in, if you want to fill in your notes, the cross-section of sphere, you would have circles. For a cross-section of a rectangular prism, if I cut this rectangular prism straight down here, then I'll get a square as a cross-section. So the connection between cross-sections and what that has to do with volume has a lot to do with how the idea of stacking up the area of the cross-section. So the first thing is, if you want to think about this cylinder here that's made up of dimes, so you can imagine that for a cylinder like this, the dimes here represent the cross sections of the cylinder. And the idea is what you do is you're stacking up the area of each of these cross sections, and they themselves form a solid, in this case a cylinder. So we're taking a bunch of area, adding them up, and that in turn gives us the volume. And there are two ways we can add or stack cross sections. You can do it horizontally, like in this example here. and then you can also stack the area vertically. So in this case, we'll be doing all the integration work with respect to x, so the endpoint should always be the smallest x value to the largest x value, and you do everything with respect to dx. If you're doing it with respect to y, which we won't do any examples of, but that's also a possibility, then if you're stacking the area or adding the area vertically, then you would use the smallest y value and the largest y value and do everything with respect to dy. So the idea of this equation that we'll use is that the integration operation, what it does is it adds up all the area of these individual cross sections, and in turn, when you add up all the area of each of these cross sections, the idea is that it gives us the volume of the solid. So if I find the area of this dime, and I find the area of the second dime, and the third dime, the fourth dime, so on and so forth, all the way to the last dime, then I will find the volume of the cylinder that's formed by the area of these dimes. So in order for us, we need to tell how far to integrate, so you need to tell what's the lower limit, which is some number here, and you need to tell to once to stop adding the area, which would be the upper limit. And what you'll be adding is the area of the cross sections. So we're going to do some examples of how to find volume, how to set it up an integral like this to find the volume of various solids. Okay, so this is example 1 in your packet, and the problem goes as follows. Write the equation for the volume of the solid formed whose cross sections are squares perpendicular to the x-axis. So there's always three main parts that you should always be given in these volume problems, which actually two. You should always be told what the cross section is. Should always be told what the cross section is, and in this case there are squares, and the axis to which it's perpendicular to, because it makes a difference if it's x-axis or y-axis, because if it's x-axis, then you'll be doing with respect to dx, and so you'll be looking to integrate from the smallest x value to the largest x value. And if it was respect to the y-axis, then you'll have you use a smaller y value to the greatest y value. So you should always look for the type of cross section and the axis that is perpendicular to. And all the examples we're doing, they're always going to be perpendicular to the x-axis, because most questions are involve the x-axis. So the first thing I'm going to do for this problem is to help you visualize what this solid looks like. It's not 100% important that you know what the solid looks like, but I think it helps a lot. So in addition to the shape of the cross section, as well as the axis to which the cross sections are perpendicular to, you should also be given an area, a specific area that always represents the base of a solid. So the base of the solid is just essentially what the solid sits on. So I'm going to try to draw this solid just so you have a visual of what it may look like, and it'll help kind of motivate the math here. So the solid here is going to be a rectangular prism because the base here is a rectangle and the cross sections are squares. So this is sort of what it looks like. I'll draw it lower. So I'm just going to draw a rectangular prism and just show you how this relates to the graph and the cross section. So what you're given in as a graph is the base of the solid. So in this case, the part that I'm shading in red, this whole part here, is the base of the solid. So what the solid sits on. So that's the base. And what you're given in the problem are the cross sections. So if I want to visualize what the cross section looks like, let's say I slice the solid here, the cross section would look like this. So this square represents the cross section. And I can draw a bunch of cross sections, and you'll notice that there'll just be squares that are congruent to each other. So this square has the same areas as this square. So what we want to do is use integration to add up all the area of the square cross section from here. In this case, according to the graph, it says the base starts at 2. So this would be where the 2 is. And then you integrate all the way up to 14. So let's set up the integration so far. So we have the integral of the lower limit, which is 2. The upper limit is 14. And this part here is always the area of the cross section. And since this is perpendicular to the x-axis, we'll have dx. So this is just the structure of the integral, just the initial structure. We're going to have to fill this in some more. So now we need to come up with an expression for the area of the cross section. So we're given in the problem that the area of the cross section is a square. So what we'll need is the area formula square. So I'm going to update this equation so that we have the formula for a square filled in. And you know the area of a square is the side length square. And so we're gonna have to figure out what the expression for the side length is. So in this diagram, the side length will always come from the base. So in this diagram, you'll see the correspondence between the graph of the base, and this works out like this. So the side length here, we see that this is 6. I'll do that in red. See, that's at 6. So the distance from here to here is 6. And then the distance from here to here is 2. Therefore, the side length of each square cross section has to be the difference between 6 and 2, which is 4. So in this diagram, we'll use this specific cross section as an example. This represents the side length of the square cross section, and we figured out from the graph that its length is 4. Okay, so all the side lengths of the cross section, as I said earlier, the cross sections are all the same. They're congruent to each other, so they're all 4. So this equation, we can fill in more information, and because we know the side length of each of the square cross section. So we'll have the integral from 2 to 14 of 4 square dx. And we can so this will give us the volume of the solid, and in this case, this is the rectangular area, the volume of the rectangular prism. So I'm going to go ahead and figure out what the volume actually is. So we're just going to integrate, so it'll be 16x, integrate from 2 to 14, and it'll be 16 times 14 minus 16 times 2, 16 times 4, this works out to be 224 minus 32, which equals to 192. So just to prove to you that this method of integration actually works, I'm going to also find the volume using the volume formula for rectangular prisms. So since we have a volume equation, so the volume of a rectangular prism, the formula is always length times width times height. So the length in this case would be from 2 to 14, that's going to be 12, times the width, which would be the 4, times the height. Since this is a square, the height and the width has to be the same, so that's also 4. And if you multiply all these numbers, you'll get 192, which matches the area, the volume that we got when we used integration. So that's a full example of how to find the volume of a solid that has a rectangular base and square cross section. You always figure out the lower and upper limit, and that will always be given by a graph. And then you're going to find the expression for the cross section. In this case, it was square, so you're going to use side square. And then we're going to have to find, if it's possible, we can find a number for the side length. If not, we'll have an equation, and you'll see an example soon. And you just essentially, at that point, if you have that set up, then you can just integrate, and that will give you the volume. So we're just going to wrap up example 1 by working more generally. So in the previous example, we had a specific lengths to work with, but that's not always going to be the case. So I'm just going to generalize by saying that this length, the distance here that was originally a height of 6, is now going to be some number given by the function f, and then that the height of 2 here is going to be given by the function g. So what I've done here is I show the correspondence. So the red line here represents this length here in the prism, and the green function g, is represented here, and that the side, one side of the square cross section is s. So it's the distance between the function f and the function g, which you can see is right here. So if I want to write an integral that's more general, that's not confined to working with numbers, then we'll set it up pretty much like the previous example. So it would always be the integral from the smallest x value to the largest x value. So from here to here, and it's going to be the area of the cross section dx, and I'm going to fill in the expression that's specific for a square cross section in our case. So it'll be the integral from x1 to x2 side square dx, and I actually know what the side length is in terms of f and g. So that means the integral can be updated to this one. So it'll be the difference between the function f and function g dx. So this difference here represents the length of the side of the square cross section. So now this you can use, got square, you can use it for any problem where you have a square cross section and f of x is the top function and g of x is the bottom function. Okay, so we're going to work on example 2. So example 2 says, write the equation for the volume of the solid formed whose cross sections are equilateral triangles perpendicular to the x-axis. So in this case, so you want to pay attention to the more important parts, which are the fact that the cross sections are equilateral triangles and they're perpendicular to the x-axis. And we also want to take a look at what the base of our solid looks like. So these triangular cross sections are sitting on this base. So just as a quick sketch for what this what this solid may look like, it'll look something like this. So this would be the base. This would be the base, and since they're a triangular cross section, it's probably it looks like it's going to be a triangular prism. Looks right. Okay, that's pretty good. So I'm gonna shade the base in blue just to make it a little bit easier to see which one it is. So here's the base, and that's what we are given in the graph. And so we have equilateral triangle bases. So it looks something like this. So the cross section are equilateral triangle, and here's an example of a slice of that. So what we'll see here, the important part to kind of get in your head is notice that the distance between the top part of the base and the bottom base is going to give us the length of the side of this equilateral triangle. So this part here corresponds, I'll do it in green. This distance here corresponds to this length here, which is the side of the equilateral triangle. So this is also S, and this is also S. So those are the side of the equilateral triangle. I'm going to take those away just so it's not too cluttered. So this is the side here. So that's a visual for what this solid looks like. It's essentially a triangular prism. And so now the important part is to set up the equation for the volume of this solid. So in this case, let's begin with by setting up the integral. So we want to figure out when to start adding the area of the individual cross sections. So here we want to go from 2 to 14. So it's going to be from 2 to 14. And I'm going to write area. We want to integrate the area of the cross section with, since they're perpendicular to the x-axis, so it's dx. And since we know the area of the cross sections here, the shape is an equilateral triangle, we actually have a formula for it, which you see right here. So we can fill that in. So it's 2, 14 root 3 over 4, the side length square dx. And based on the graph, we can update this equation even more because we can figure out exactly what the side length is. So the side length, remember, is the distance from the top part of the base to the bottom part of the base, which corresponds from here to here. So we don't need to know the difference between 8 and 2, which will give us this length, which is the same, which corresponds to the side length. So 8 minus 2 is 6. So I can update this to 2 to the 14 root 3 over 4 times 6 square dx. So when we integrate this, and I'm not going to do that out, but you can do that with your calculator, you will get exactly 108 root 3, which is approximately 187.06. So just to prove to you that this actually works using the formula for a triangular prism, I'm going to use Google to look up the calculator that does this. So volume of a triangular prism, and I'm gonna punch in all these numbers. So the volume looks like this. So I'm not gonna do that out by hand. I'm gonna plug it in. So the base of the triangle in this case was going to be 6. I'm gonna put 6 here, and the other side of the cross section, since it's an equilateral triangle, also be 6, and this will also be 6. And the height would be the distance between the two bases, which is from 2 to 14, and that's 12. And we get, Google tells us that the volume of this triangular prism should be 187.06, which matches the result if we use integration. So integration does work to help us find the volume, and it fits in with, it gives the same result as the formula for the area of a triangular prism, which is this. So it works. So I'm going to do this problem just like the previous one. I'm going to be much more general because we're not always going to be having some specific number to work with. So it'd be nice to just generalize what this formula could be. So I'm going to start from here. I'm going to, the x value, just say it's x1 to the highest one's x2. It's going to be root 3 over 4. And the side length expression here would be, so the top part of this base is going to be given by the function f, and the bottom part of this base is going to be given by function g. Just like this one, the side length will be of the triangular cross section will be given by the distance between f and g, so that's going to be s. So I'm going to fill that in. So the side length is going to be f of x minus g of x square dx. And I'm going to just take out the constant because if there was actually functions to work with, it'd be easier to have the constant in the front. So it would be x1 to x2 f of x minus g of x squared dx. And that will be the general formula you could use to figure out the volume of a solid that has a cross section that are equal at a triangle. And there you go. So for example 3, it is write the equation for the volume of the solid formed whose cross sections are squares that are perpendicular to the x-axis. So pay attention to the cross section. There are squares. It's perpendicular to the x-axis, and we're given the graph of the base of the solid, which is this. So this is a little bit different from the other one in terms of we have the side of the base of the solid are controlled or given by two functions. In this case, this is function f, which gives us the length of the side of the base of the solid, and g of x gives us this side of the solid. So just as an attempt to kind of draw what this prism could possibly look like. Here I've drawn the base a little bit angled here just so we can draw the cross section. So this part here, this side, corresponds to f of x in this drawing, and g of x corresponds to this. So that's g of x, and this is f of x. And one example of the square cross sections, I'm not going to be able to see what this solid looks like, but that's not important. I'm going to draw the cross section here. So it's a square. So there's a square cross section. So the important thing to notice, or at least kind of see in your head, is that the side length of this square cross section is the distance again between function f and function g. That's s. And then this will be s, and this is s. So we have lots of cross sections, and what we want to do is find the area of the cross sections and then individually, and then add them up. And integration will do that for us. Assuming that this is a square, you notice that the side length of the square cross sections are going to be different depending on where you want to look at the cross section. So the square cross section looks like this, side length is that, but when you get to this point, the side lengths of the square cross section is going to be bigger because the distance between f and g gets bigger. And so if you want to draw the cross section, it looks something like this. So you can see the area of the cross section at this point is much bigger than the area of the cross section earlier. So how do we actually deal with that? Because before, the cross section side lengths were all the same, and now it's varying. So all we need to do is just make sure we have an expression for the changing side lengths. So since the side lengths here is always going to be, there's a distance between f and g, s is always going to be this equation. So it will be 1/3 x plus 2/3 minus g of x, which is negative 1/3 x plus 10/3. So And then this simplifies to be 2/3 x minus 8/3. So this will always be the side lengths, no matter no matter what x value I choose. So I can choose an x value here. If I plug the x value into here, that's going to give me automatically the side length of that new square cross section. So this is the expression. This will give us a side length at any given x value. So to put this together, to get the volume, we start the same way like the other one. We want to make sure we integrate. We want to figure out when to start adding those areas. In this case, we're going to start at 4, and then we stop at 16. And we want the area of the cross section dx, and we know the area of the cross section, the shape of it is for a square. So that would be the integral from 4 to 16 of side square dx. So now we have an expression for the side, which is this. So we can integrate from 4 to 16, 2/3 x minus 8/3 square dx. And if you use your calculator to integrate that expression, you'll get 256. So you go ahead and type that into the graphing calculator and you should get 256. So just to summarize, the big point here is to figure out how to get an expression for the side length, which is always the difference between f and g in this case, because f is on the top, g is the bottom. If you find the difference, that's always going to give us the side of the square cross section. So here or here. So that's the expression for it, and we can just plug it into the integral. So the smallest x value here is 4, the greatest x value is 16. The expression for the side of the square is this one right here, and make sure we square because it's side square. And when you integrate this into a calculator or by hand, you should get 256. So for example 4, I'm not going to be doing this problem out because it's pretty similar to the previous example 3. The only difference is that now the cross section is a different shape. In this case, it's a semicircle. And so for the semicircle, the area for the semicircle is pi over 8 times the diameter square. So you guys should try setting up that problem, and when you evaluate your integral, you'll know you got it right if you got an answer of 100.531. I'm going to move on to example 5. Just because the graph is a little bit different from the other ones you've seen, but the concept is the same. This is an example of like where your base is a weird shape, and it gets to a point where it's very difficult for me to draw a picture of what the solid would look like. Nearly actually impossible to draw it. But all we need to know is again what the base looks like and what the type of cross section it is, and what the cross sections are perpendicular to. So I'm going to think the one before this says the cross sections are squares. I'm going to skip that because we've been doing a lot of squares. I'm going to do the second part, which is the area of the cross section. The cross sections are isosceles right triangles. So to read this problem, just make sure we're paying attention to all the important things. This is our base. Our cross sections are isosceles right triangles, and they're perpendicular to the x-axis. So just to kind of doing these problems efficiently, you want to be able to really fast identify what part would give us the side lengths. So the distance, again, the distance between the cross section, the would be here. So the bottom part of the cross section would be here. And that will give us S, which corresponds to this. So I can't really draw the cross section, but if you can imagine there's a right triangle that's kind of coming out, and this is the side of the one side of the isosceles right triangle. So that's S. So we know S is always going to be given by the difference between these two, distance between these two functions, which is going to be sine pi x minus x cubed minus 4x. So make sure you put parentheses around here because there's two terms. And I'm just going to simplify this for the side. So it's going to be sine of pi x minus x cubed plus 4x. So that's the expression for the side of the isosceles triangle. And I'm going to write the integral statement now. So I'm going to integrate from the smallest x value, in this case it's 0. So I'm going to put 0 to the largest x value, so that's 2. The area for the cross section is here, so I'm going to put 1/2 side square dx. And since we have the expression for the side length, which is right here, I'm going to fill that in. So that's equal to the integral from 0 to 2. I'm going to take out the 1/2, put in the constant in the front, and I'll plug in the side expression, so sine of pi x minus x cubed plus 4x square dx. And when you integrate this, that's going to give us the volume of the solid, and that's going to be equal to 4.989. So those are all the examples. Hopefully that's enough for you guys to be able to work do the homework on your own. So just to remind you what the homework looks like. That was the last example. So the homework are a total of 4 problems. You guys have more information on yours. You have actually my handwriting here with the intersection points. So make sure that you write the expression for the volume and not just the answers. And you also have the answers in your packet, which is right here. And then also make sure you guys do the third part of the homework, which is to make sure you know how to find intersection points with a graphing calculator. So make sure you watch those 2 videos, and then make sure you do the homework and watch the videos, and make sure you're prepared for a mini quiz on Monday to make sure that you guys did this lesson. If you guys have any questions, you can text me with anything, and hopefully these videos were clear enough.